Hi everybody, and welcome to another episode of Math with Mr. Emond. Today we're going to be starting a new unit on set theory and logic. Now we all know what sets are. Here is a set of Russian dolls. A set in math we're going to call a collection of distinguishable objects. So for example, in math we might have whole numbers as being a set. Right? And whole numbers are any numbers from 0 to infinity. We can think of other sets that we could describe in math, like for example, what about natural numbers? Natural numbers are any number from 1 to infinity. What's the difference between a natural number and a whole number? 0 is not included in natural numbers. What about integers? This could be a different set, right? Integers are anything from negative infinity to positive infinity, right? So we can start to think of different kinds of sets in math and different kind of sets in the world, like a set of Russian dolls, a set of playing cards. Right? You can think of a million examples of things that could be sets. Now an element is just an object in a set. So for example, 3 is an element of W. 3 is an element within the set W. What about 0? Is 0 an element of W? Yes. Is 0 an element of N? No. Is 0 an element of I? Yes. Universal set. What is that? Well, a universal set is a set of all of the elements that are under consideration for whatever context we're talking about. So if we're talking about a deck of cards, what is the universal set? Well, it's every single deck, every single card within that deck. All of the hearts, all of the spades, all of the diamonds, all of the clubs together. Another example would be the universal set of digits, right? All in the universal set of digits is 0 to 9, right? But we could break this up, right? Rather than talking about all the digits from 0 to 9, we could maybe talk about subsets of it. So for example, well, first, a subset is a set whose elements all belong to a different set. Okay? The universal set of digits is everything from 0 to 9, but we could also talk about only the odd digits, right? And we might label that as O. Now, the odd digits are 1, 3, 5, 7, and 9. All of the odd digits fall within the universal set of digits, but does not include all of the universal set, okay? Because you have odd digits and even digits, and those together make up all the digits. So a subset is a small group within the larger group, right? And we would write that by saying our odd set O is a subset, and that's what this sideways U thing is. It means subset. O is a subset of D, which is all digits. Okay. What about complements? So a complement is all of the elements of a universal set that don't belong to a subset of it. So for example, we had the odd digits. What is the complement of the odd digits? So the complement of the odd digits, and the way we say complement is with this apostrophe here. So O apostrophe means the complement of O, or the complement of the odd digits. And what are those? Well, all the even numbers and 0. Okay? So if our odd digits is 1, 3, 5, 7, and 9, the complement of the odd digits is all the digits in the universal set from 0 to 9 that aren't found in this set. What about an empty set? Well, an empty set is a set that doesn't have any elements in it. So for example, the set of odd numbers, so again, we're dealing with these numbers here. The set of odd numbers which are divisible by 2 is an empty set because none of these numbers are divisible by 2. Anytime you try to divide them, you get a decimal answer or a fraction, right? So that would be an empty set. Disjointed sets are sets, there could be more than two or more sets that have nothing in common, no elements in common. For example, if we were going to look at O, which is 1, 3, 5, 7, and 9, and E, which is 2, 4, 6, and 8, well, these two sets have nothing in common. They are disjointed. And one final thing here, in set notation, the number of elements of a set is written as n of x, right? So how about this? The number of elements within O, there's 5, right? 1, 2, 3, 4, 5. The following is a summary of notation introduced so far. Okay, so your universal set, in this case, would be 1, 2, and 3, right? I know I'm talking about the universal set because of the U here, right? And this is set notation. Remember, we use our brackets. We separate the elements by commas. To define a set A that has only the numbers 1 and 2 as elements, you would write A is equal to, well, 1 and 2, right? And because 1 and 2 are part of the universal set, you could say A is a subset of U, right? And what would be the complement of A? Well, it's everything that's not in A that's also part of U. So the complement of A in this case, so the complement of A in this case would be just 3. That's the only element not a part of it. And B, well, B has no elements, right? Between A and the complement of A, we have everything. B has nothing in it. So we could either write it like this, you know, like B is empty, or we could write it like this. B is empty. Doesn't matter which one you do. We have finite sets. A finite set is a set that has a countable number of elements. So for example, the set of even numbers has 4 elements, 2, 4, 6, and 8. An infinite set is a set that has an infinite number of elements. You can't possibly count them all. Like for example, natural numbers go from 1 to positive infinity. How many numbers is that? Who knows, right? You can't count it. It goes on forever. That's an infinite set. Mutually exclusive. Mutually exclusive means when you have 2 or more events that cannot occur at the same time. So for example, the sun rising and the sun setting are mutually exclusive events. They can't happen at the same time. Okay, let's look at this example. Brooke drew the following Venn diagram. This one right here. In this Venn diagram, she described the sets as following. C looks like it's her universal set, and C was all the produce that she bought in the grocery store. She split C up into what looks like 3 different subsets. Her first subset was F, so F is all of the fruit. And all of the fruit included oranges, pineapples, bananas, apples, and pears. Notice I said these because they're within the larger circle F, which means they're a part of F. S are the fruits that you can eat without peeling. And so the fruits that you can eat without peeling are apples and pears. Is that true? Yeah, you have to peel these ones. Okay. And V are vegetables like peas, carrots, potatoes, corn, and beans. Now these are traditionally called vegetables, but the botanist in me is saying actually peas, corns, and beans are fruits, not vegetables, which they are. They're fruiting bodies, right? So they're fruits. But in society, we tend to call them vegetables. So I'll let that slide, Brooke. That's okay. Do you agree with her descriptions? Let's go with yes. I agree with them, except I don't, right? because the biologist, the botanist is me saying, no, these are fruits. But let's go with yes. Describe another way Brooke could define the sets in her diagram. Well, we could have done something like this, where C is all the produce, but instead of splitting it into fruits that have to be skinned and fruits that don't, and then vegetables, we could have said, well, let's instead have the orange produce, right? Things like the oranges and carrots, which are orange in color. And then have yellow ones, bananas, pineapples, and corns. And then green ones, apples, peas, and beans. And then brown ones, potatoes and pears, right? So we could have split it up like that. And there's a whole bunch of other ways that you could have potentially split her sets in the diagram. Why does it make sense that S is a subset of F and S is a subset of C? Okay, well, that's an easy one. S is a subset of F because all fruits that you eat without peeling, like apples and pears, well, they're still fruits, right? Just because you don't have to peel them doesn't mean they're not fruits anymore. They're still fruits. So S is a subset of F. And S is a subset of C because even though these are the fruits that you don't have to peel, they're still produce, and that's all C is, right? So of course, S is a subset of F, and S is also a subset of C. List the disjointed sets if there are any. Well, F and V are disjointed, right? And S and V are disjointed. I can see that, like they're not connected at all, right? F is not connected to V and S is not connected to V. Is the complement of F equal to V? Well, the complement of F would be anything not within F that's also part of C, that would be V, right? Yeah. Determine the number of items in V using the number of items in F and the number of items in C. The number of items in C is equal to the number of items in F plus the number of items in V. So here I've written a statement using the terms they want me to use, right? If I take this orange circle and the teal circle and I add them together, I have everything within C, okay? So how many items were in F? There's 5 of them. Orange, pineapples, bananas, apples, and pears. How many items were in everything? 10. If I somehow didn't know this, which I mean, obviously I do, but if I didn't know it, I could still calculate for it, right? 10 minus 5 equals X, X equals 5, where X is the number of items in C. List the elements in the complement of S. Okay, the complement of S is everything not in S that is part of C. So it's your oranges, your pineapples, and your bananas, and your peas, and your carrots, and your potatoes, and your corn, and your beans. Okay? There we go. Draw a Venn diagram to show the universal set U, and U being natural numbers from 1 to 40. E is going to be our multiples of 3, and F is going to be our multiples of 15, and S is going to be our multiples of 9. Okay, here we are. So here's our Venn diagram. U is every natural number from 1 to 40. Okay, so they're all there. E, this big circle, is going to be multiples of 3. So we have everything from 3 up until 39. Every number from 3 to 39 is here. Okay, so we have 3, 6, 9, 12, 15, 18, 21, 24, 27. Where's 30? 30, 33, 36, 39. They're all there. F is multiples of 15. Well, so multiples of 15 is going to be 15 and 30. Okay, so 15 and 30 are here, and S is multiples of 9. So 9, 18, 27, and 36. So here's our Venn diagram. List the disjointed subsets if there are any. F and S are disjointed subsets. There's no overlap between the two. Either you are a multiple of 15 or you are a multiple of 9. There is no multiples of 9 that are also multiples of 15. So S and F is our answer for A. Is each statement true or false? And explain. Is E a subset of F? Is E, this large thing that encompasses all these numbers, is it a subset of S? Do all the numbers of E fall within F? No. No. F only has 2 numbers. So of course, all the numbers of E don't fall within F. The reverse is true. F is a subset of E, but not the other way around. So false. Number 2, B2. Is S a subset of E? Is S, this teal circle, a subset of E? Yes, of course it is, right? E are multiples of 3. Is 9 a multiple of 3? Yes. Is 18? Yes. 27, 30. Yeah, these are all multiples of 3. Okay? True. All elements of S are in E. Is S a subset of F? Is S a subset of F? No. They're disjointed sets. There is no time when a multiple of 9 is also a multiple of 15. False. And is S a subset of S? Are all the numbers, so think of it like that's kind of a weird way to ask a question. But that's basically saying, are these numbers 9, 18, 27, and 36, the numbers within S, are they also within S? Well, duh. Of course. True. A set is a subset of itself, right? It's kind of repetitive thinking, but yeah, of course. And lastly, F, the complement of F. Okay, what's the complement of F? It's all numbers from 1 to 40 except 15 and 13. Yeah. Is that true or false? Yeah, that's true, right? The complement of F is every number in the universal set that's not in F. So every number from 1 to 40 except 15 and 30, that's true. Yeah. You bet. Okay, it's your turn. Go ahead and pause the video now, work out these problems, and come back when you're ready. Okay, welcome back. Let's go through the answer. So for part A, we wanted S to be the universal set and for it to be all natural numbers from 1 to 500, and they wanted us to represent it using set notation. So there was actually 2 ways you could have done this. Here's the first way. You just say S is equal to these elements, 1, 2, 3, carrying on to 498, 499, 500. Now you could have done 1, 2, carrying on to 499, 500. It doesn't really matter, but there should have been a little bit of a gap here because you don't want to write all 500 numbers. That's going a little bit crazy. The other way you could have done it is speaking like a mathematician. X such that, this long line means such that X is going to be in between 1 and 500 and it can be equal to them, right? So this is X is greater than or equal to 1 and X is less than or equal to 500, which means X is sandwiched in between 1 and 500. And X is an element of natural numbers. So this is a mathematical way of saying X is every natural number from 1 to 500, basically. Let's look at part B. Indicate the multiples of 5 and 10 from 1 to 500 using set notation. So you're going to need probably more than one set, right? You'll have the set of numbers that belong to multiples of 5. You'll have the set of numbers that belong to the multiples of 10. And you'll probably have the set of numbers that belong to neither of those. Here's the first one. So I defined F, the subset F, as the set of multiples of 5 from 1 to 500. And so here's your normal set notation, 5, 10, 15, carrying on to 490, 495, and stopping at 500. Now the other way to write this is with a math expression. So here we have the subset F is equal to f such that f is equal to 5 times x. So x is a variable. Let's look at what that means. When x is 1, what's f? 5. When x is 2, what's f? 10. When x is 3, what is it? 15. So all of those numbers fall within f. Now, x isn't every number ever. X is any number between 1 and 100. So on the small end of the scale, when x is 1, that's 5. That's my smallest number. And on the big end of the scale, 100, what's 100 times 5? 500. And that's my big number. And we have every number in between those because we're saying that x can be any natural number. So x can be 50, right? And 50 times 5 would be 250, and that number belongs in there too. So this is the mathematical way of saying it. F is a subset of S, right? S was all the numbers in the universal set. And of course, the multiples of 5 are a subset of all of those numbers. The next subset would be the multiples of 10. And so you could have written out like this, and then the math speak is, t such that, and you could have changed these, right? You don't have to call them f and t. They could have been whatever you labeled them as. T such that t is equal to 10 times x. This time the limits on x are different, right? And to figure out your limits, just think of what's the smallest it can be? Well, 10, right? 10 times 1. What's the biggest this number can be? 500. So 500 means x can be no bigger than 50 because 10 times 50 is 500. But x can be any number within those as long as it's a natural number. And of course, t is a subset of f, right? All the numbers of t are also numbers of f, and t is also a subset of s. And then finally, if you're not a multiple of 5, then you're a non-multiple of 5. So that's my last subset, or I could call it the complement of f, right? So any number that's not part of f is the complement of f, and f and the complement of f make up the universal set. And there's no way I could have come up with an algebraic expression for it, so I just wrote a description that says the complement of f is non-multiples of 5 from 1 to 500. Now you were asked to represent the sets and subsets in a Venn diagram. So here's my Venn diagram. I had the universal set here, labeled as S. Then in blue, I had the set F, which F was defined as the multiples of 5. So all the numbers within F are my multiples of 5. Now my multiples of 10 are here in T, and remember all of my multiples of 10 are also multiples of 5. So T is a subset of F, and F is a subset of S. Anything that's not a multiple of 5 belongs to the complement of F. And together, all the numbers of F and all the numbers of the complement of F belong to my universal set. And that's it. So here we go. Our key ideas and our need to knows for the lesson are here. For practice, I would like you to do practice 1. You will find practice 1 on Schoology. So if you go to this folder for outcome 3, application of set theory, you'll find everything for this unit. Here's your practice questions. It's literally the first thing that you're required to view. Now, one thing to note is that these practice questions are the practice questions for the whole unit. So when you scroll down, you'll have your notes for the first lesson, and then practice 1, the questions that go along with the first question. And then it goes to the notes for lesson 2 and the practice questions for lesson 2, etc. until we finish the whole unit. So you'll want to keep coming back to this to view the questions that are required for homework. Lesson 1, this is where the video is going to be posted. Of course, I'm still recording it, but when I'm done, the video will go here. And this was an in-class investigation that we would have done during class time. So if you missed class, if you weren't here when we did that, you can find a link to it and an embedded file here. Go ahead and try it out yourself. Get some practice with sets before you try your homework. And then of course, once you finish practice 1, here's where you're gonna hand it in. Submit a picture of your work. You're gonna have to do the work on loose leaf. Once you're done, take a picture of it with your phone and upload it on the Schoology app on your phone as a picture, as evidence of your work. That's it for today. See you guys next time. Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end, and over here, you will find the next video in this unit. Keep learning, everybody. Take care.